Welcome. In this section, we're going to be talking about ellipses and circles. So this is part of our discussion of the conic section. So we'll begin by doing a quick review of circles. And so to start that off, we will look at their geometric definition. So we want to recall that a circle is just the set of all points in the plane equidistant from a fixed point, which we call the center. So when we look at the graph of a circle, we have a point right in the middle here, the center, and ordinarily that point is denoted by the coordinates h and k. And so the circle itself is just the set of all points that are equidistant from this point. So when we look at the distance from the center to a point on the circle, that distance, of course, is the radius, which we call r. And so you may recall that the standard equation of a circle is given by x minus h squared plus y minus k squared is equal to r squared. And so again, the coordinates hk give us the center of the circle, and r is the radius. That's the distance from the center to any point on the circle. And so we'll want to remember how to graph equations of circles. So as an example here, suppose we had, let's say, x plus 3 squared plus y minus 1 squared is equal to 9. So first we'd want to identify the coordinates of the center, which would be h and k. In this case, the center would be at -3, 1. And so remember that when we're finding h and k in the standard equation, you have x minus h and y minus k as the quantities being squared. And so that basically means that when we're finding h and k, we want to take the opposite signs of the numbers that we see in the equations. So for the x coordinate here, we take -3. For the y coordinate, we're taking +1, just changing the numbers 3 and -1. Changing their signs when we identify the coordinates. Anyway, for the radius, notice that r squared is equal to 9, and so that of course means that r itself would be 3. And again, notice that we do not write r as plus or minus 3, r is a distance, so it's always considered to be a positive quantity. Anyway, so if we wanted to graph this equation, we simply want to use our center and radius here. So we know the center's at -3, 1, so it would be this point right here. And the radius is 3, so we simply want to count 3 units in every direction. So I'll go a little bit off my grid here to sketch the graph of this circle. That should look something like this. So this is just going from the center at -3, 1, 3 units in every direction, left and right and up and down, and then we're simply connecting the 4 points that we just drew with the graph of a circle. And as always, when we're graphing equations, we're just looking for rough sketches, so these do not need to be perfect circles by any means. But your graph should be at least somewhat accurate. Okay, we should also remember how to rewrite equations in standard form by completing the square. So we'll take a look at an example of how this works. This will give us a quick review of completing the square as well. So suppose I had the equation, let's take x squared plus y squared, minus 4x plus 2y plus 1 is equal to 0. So the first thing to do here would be to rearrange the terms. I want to group up the x terms from the y terms. So I'll rewrite this as x squared minus 4x. I'll leave a little bit of space here so I can complete the square, and then we'll have y squared plus 2y. The constant of 1 that I see at the end, I'm going to go ahead and subtract that over to the other side. So we just want to have the terms containing x or y on the left-hand side. Any constant terms should be moved over to the right-hand side. So remember that to complete the square, we want to take half of each of these coefficients of x and y and then square them. So for the x terms, I'm going to take -4, divide that by 2, that gives me -2, and then I need to square that result. So that means that for the x terms, I'm going to need to add 4 to them. Then I do the same sort of thing for the y terms. I want to take the 2 that I have here, take half of that, which of course is 1, but then I need to square that result, and 1 squared is still 1, so I would need to add 1 to the y terms also. Okay, well, since we've added 4 and we've added 1 on the left-hand side of this equation, we simply need to add 4 and add 1 on the opposite side as well. Now we can factor the x terms. X squared minus 4x plus 4 factors as x minus 2 quantity squared. And for the y terms, we will have y plus 1 squared. And on the right-hand side, we have -1 plus 4 plus 1, which of course just becomes 4. So this gives us the equation of this circle in standard form, so now we can easily identify the coordinates of the center here, which would be at 2, -1, and our radius this time, hopefully is easy to tell, it's just going to be 2. And for more practice here, let's go ahead and graph this circle as well. Our center this time is at 2, -1 down here, and then the radius is 2, so again, from our center we count 2 units left and right, and 2 units up and down, and then we just want to connect those 4 points by drawing a circle. So that would be the graph of that. Okay, well, circles are very closely related to ellipses. In fact, there are special types of ellipses, as we'll see. So let's go ahead and define ellipses next. So we say that an ellipse is just the set of all points in the plane, the sum of whose distances from 2 fixed points, which are called the foci, is constant. So what exactly does this mean? Well, let's take a look at a graph here so we can understand what exactly is going on. So an ellipse is basically an elongated circle. It's an oval shape, in other words. So it's like we're taking a circle and just sort of stretching it out. But the way the ellipse is generated is by looking at these 2 fixed points, which I'll label as F1 and F2 here. So each of the points F1 and F2 is a focus of the ellipse. And so the plural of that is foci, or also pronounced foci. But there's always these 2 points here that generate the shape of the ellipse. And so what exactly is happening is that if I look at some point on the ellipse, say look at this point A, I want to take the sum of the distances from that point to the fixed points, F1 and F2. In other words, what I'm looking at here are the lengths of the segments AF1 and AF2, and I'm adding those segments together. Well, that sum, whatever it turns out to be, would have to be the same for any other point on the ellipse. So if I look at another point on the ellipse, say this point B here, I could measure the distance from B to F1 and from B to F2. So again, just basically adding the lengths of these segments together. That would have to be the same as the sum that we got looking at the distances from A to F1 and A to F2. So any point that I choose on the ellipse, if I take its distance from these 2 fixed points, F1 and F2, and add those distances together, that'll be the same as it is for any other point on the ellipse. So again, each of the points, F1 and F2, is called a focus. And again, the plural of that word is foci, as we mentioned before. The same way that cacti is a plural of the word cactus. Similar idea. Okay, so again, circles are just special types of ellipses. In fact, if F1 and F2 are the same point, then what we have is a perfect circle. And in fact, if F1 and F2 were the same point, then they would both lie on the center. So the center in both foci would be the same when you're talking about a circle. So a circle is just a special type of ellipse that has this property, that both of the foci are the same. And so we'll use the equations of circles to understand where equations of ellipses come from. So again, for circles, just to reiterate, we have the standard equation x minus h squared plus y minus k squared equals r squared. So again, h and k form the center and r is the radius. And so again, if we look at a graph of a circle here, we have our center at hk. And then the radius r here, that's going to be the same in any direction. So whether you're going up or down, left or right, or any other direction for that matter, you would always go the same distance r to locate a point on the circle. So to understand equations of ellipses, what we're going to do here is to take this equation, and we're going to divide everything by r squared. So I could rewrite this equation as x minus h squared over r squared plus y minus k squared over r squared is equal to 1. Well, for ellipses, it's a similar idea here. The only difference now is that we're looking at two different distances when we go in each direction. So for ellipses, if we're measuring from the center, which we're still going to identify by the coordinates hk, then we have these two different distances. I have one distance a, which gives me the horizontal distance from the center to a point on the ellipse, and I have a vertical distance, which I'll call b. So these kind of take the place of the concept of the radius when we're looking at the circle. And so an easier way to remember how we get the equation here for ellipses is we take the x minus h squared, and instead of dividing by r squared, we divide by a squared. We divide by the distance that we're going in the x direction, in other words, going left or right. For the y minus k squared, again, we don't divide by r squared like we do with circles. We're now going to divide by b squared instead, because that is the vertical distance. That's how far up or down that we go from the center, and that's just going in the y direction. So this gives us the standard equation that we use for ellipses. Again, very similar to equations of circles. We just need to note that we have these two new distances, a and b, that we use for actually sketching the graphs. So next, let's take a look at actually sketching some graphs here. Suppose I had the ellipse, let's say x minus 1 squared over 9 plus y minus 3 squared over 4 equals 1. So for ellipses, what we want to do here is to identify the center as well as the values of a and b. So the way we find the center is the same thing that we had done for circles. We're still looking at h and k. And so in this case, that would be 1, 3. For a squared and b squared, though, notice that a squared is 9 and b squared is 4. But to actually graph the ellipse, we just want to know the a and b values themselves. So we know that a is 3 and b is 2. And so again, these a and b values will tell us how far left and right and how far up and down from the center we go to identify points on the ellipse itself. So let's go ahead and take a look at the graph next. So again, we identified the center as being at the point 1, 3. So that would be right here. Then we know that a is 3. So from our center at 1, 3, that means we go 3 units to the right and 3 units to the left. Our b value is 2. So again, measuring from the center, we go up 2 units and down 2 units. So it's these 4 points that we've just created that we use to graph the ellipse. And so it's just drawing an oval, basically, going through those 4 points. So not too different from how we graphed circles. Again, the only real difference is that we're not going the same distance in every direction. We have these two different distances. We have an a distance, which is the distance we go horizontally in the x direction, and a b distance, which is the distance that we go vertically in the y direction. Let's try some other examples. How about if we look at the equation, let's say x minus 2 squared plus y squared over 4 equals 1. So here it can be helpful to rewrite the equation. You won't see it printed this way in the textbook, but if you like, you can go ahead and take the x minus 2 squared and put that over 1 to remind us that the a squared value in this case would be 1. And so when we're looking at the coordinates of the center here, our h value, hopefully is not too difficult to tell, is 2. But notice that for the y term, we just have y squared. And so we can recognize that the k value in this case will be equal to 0. So that's the coordinates of the center. And as we mentioned, a squared is equal to 1 and b squared is equal to 4. And so that means that a itself will be 1 and b will be 2. And so again, we can use this information in order to sketch our graph. So starting from our center at 2, 0. Again, a is 1, so we simply count to the left and right from our center 1 unit. B is 2, so we go up 2 units and down 2 units. So we have this rather small ellipse right here. So that's how we sketch graphs of ellipses. Next thing we'll do is to analyze various properties of ellipses that we need to be familiar with. And so when we look at ellipses, we can basically have ellipses that are elongated horizontally, like so, or we can have ellipses that are elongated vertically, like this one. Again, in each case, the center will be at HK. For the first one, we have this distance here, A, that goes in the horizontal direction, and we have this other distance, B, that goes in the vertical direction. But what we want to imagine next is if we were to extend those segments in the other directions. So if I take the A value and I extend it the other way, that gives me a line segment that goes all the way through the center of the ellipse. And I could do the same thing with the B value here, extending it downward, so that it also goes all the way through. Well, those two segments give us what we call the major and minor axes of the ellipse. So this horizontal distance going all the way across, that would be the length of the major axis. And the vertical distance in this case would be the minor axis. And so for this first ellipse here, we can say that the length of the major axis is just going to be 2 times A. Because all we're doing is taking the segment A and extending it in both directions, so we're doubling its length. And in a similar idea, the minor axis would have a length of 2b. For our other ellipse, though, which is elongated in the vertical direction, well, this time our A distance is going to be shorter than the B distance. And so in this case, if we were to extend B all the way across and also extend A all the way across, those would still give us the major and minor axes, but they're kind of flipped around here. In this case, the vertical distance would give us our major axis, and the horizontal distance would give us our minor axis. And so in this case, the major axis has a length of 2b, and the minor axis has a length of 2a. So the major and minor axes are kind of similar to the idea of a diameter of a circle. Again, they're just line segments that extend all the way across the object, going through the center. But you just want to remember that their lengths are simply the double of the values of A and B. And which one is considered the major and which one's considered the minor is simply a matter of which one's longer. The major axis will always be the longer axis. The minor one, of course, will be the shorter one. Another term that we need to be familiar with are the vertices of the ellipse. So the word vertices, this is simply the plural of the word vertex. So we can talk about one vertex or two vertices. Well, the vertices of an ellipse, these are just the endpoints of the major axis. The endpoints of the minor axis, some textbooks refer to them as the covertices. Most textbooks actually don't really give them a special name, though. They just call them the endpoints of the minor axis. When we're talking about the vertices themselves, though, we're talking about the endpoints of the major axis always. So make sure you remember that it is the major axis that are the vertices, not the minor axis. But as long as we know where the major axis is, then we simply have to locate its endpoints to describe these points. The last thing we're going to look at here is how we find the foci. So remember, the foci were the two fixed points that generate the ellipse in the first place. And so it's important that we understand how to locate those. Well, to do that, we have to use the quantity c, which gives us the distance from the center to each focus. And so how do we calculate c? Well, it comes from using the Pythagorean theorem, but basically it works out to be c is equal to a squared minus b squared, and then we take the square root of that. We do that if the a value is larger than the b value. If b is larger than a, then we would have to do b squared minus a squared. We obviously want to make sure to subtract the smaller number from the larger one so that we're taking the square root of a positive value. We don't want to take the square root of a negative, since that would be an imaginary quantity. And c is never going to be imaginary. This is always going to be a real number. It's going to be an actual distance from the center to each focus. Okay, so let's go ahead and take a look at an example of working with the equation of an ellipse and also identify all these important features that we've just mentioned. So the next thing we'll take a look at here is the equation x minus 1 squared over 9 plus y plus 3 squared over 25 is equal to 1. So the first thing to do, as we saw before, is to graph this thing. And so we want to identify the coordinates of the center, which in this case would be at 1, negative 3, as well as our a and b values. So a squared we can see is 9, that tells us that a is 3, and the b squared value is 25, which tells us that b is 5. So taking a look at our graph next. Again, our center is at 1, negative 3. A is 3, so I want to count to the left and to the right 3 units. B is 5, so I'll need to count up 5 units and down 5 units. And again, I just need to connect these 4 points with the graph of my ellipse. So it should look something like this. Okay, so to identify the important features of the graph, notice in this case that our major axis is just going to be the longer of the 2 segments that go through the center of the ellipse, but that's just going to have a length of 10 units. And notice I'm just taking the b value and doubling it. B is larger than a in this case, so taking 2 times b gives me the length of the major axis. And for the minor axis, well, that's just the length of the shorter segment that goes through the center, which in this case would have a length of 6. And again, notice there that I'm just taking the a value and doubling it. For the vertices, those again will be the endpoints of the major axis. So I want to look at my graph here. These points at the top and bottom, I'll label each one as V for vertex. Those are the vertices. They're just the endpoints of the major axis. So I simply want to give their coordinates. The vertices in this case would be at 1, 2, and 1, negative 8. So when we graph our ellipse, it should be very easy to identify the vertices. We're just looking at the endpoints of the major axis. The last thing we need to look at here are the coordinates of the foci. And so in this case, what I want to do to find C is to take the square root of b squared minus a squared. But really all I have to do is to go back and look at the denominators of the fractions in the original equation, which were 25 and 9, and I want to subtract them. And when I do that, I want to make sure I'm subtracting the smaller one from the larger one. Obviously, I don't want to do 9 minus 25. That would give me a negative number, which would result in an imaginary value when I take the square root. So obviously, I want to do 25 minus 9. But if you go back and look at the original equation, it's just looking at the quantities that you have in the denominators. And we're simply subtracting those. So this gives me square root of 16, and of course that will simplify to 4. Now I'm not finished yet. This doesn't tell me the actual coordinates of the foci. Again, this C value is just the distance from the center to each focus. So that tells me that the foci are each going to be 4 units from the center. So what we need to realize here is that the foci, they're going to be 4 units above and below the center. So in this case, if I count 4 units up, I'll have one focus here. If I count 4 units down, I'll have another focus here. And so the coordinates of the foci, in this case, will be 1, 1, and 1, negative 7. So the foci are always going to be in the same direction that the vertices are. In other words, they're always going to be located on the major axis, just like the vertices are. So the vertices and foci should always be going in the same direction from the center. And that's an important thing to remember. Everything's always kind of done in respect of the major axis. The vertices and foci will always be along the major axis. But again, we just use this value C to determine how far each focus is from the center, and that allows us to identify their coordinates. Now in this example, when I found C, I ended up getting a whole number for it. Very often we're going to end up with radical values for C, in which case we'll just identify the coordinates of each focus. We won't necessarily actually graph them. But we should always be able to give the coordinates of each focus, if nothing else. And so we'll see that sort of thing with our next example here. So let's take a look at the equation x plus 2 squared over 36 plus y squared over 16 equals 1. So the center in this case, hopefully we can see, is at the point negative 2, 0. And as before, we want to identify our a and b values. So in this case, a squared we can see is 36, making a equal to 6. B squared is 16, which makes b equal to 4. Okay, so taking a look at our graph, we will see the following. So again, center is at negative 2, 0. A is 6, so I want to count 6 units to the right and 6 units to the left. B we said was equal to 4, so that means I'm going to be counting up 4 units and down 4 units. So we end up with a pretty large ellipse this time. Hit sketch in our graph. So it should look something like this. Next, we'll identify the lengths of the major and minor axes. So for our major axis, again, we're just taking the a and b values and doubling the longer one. So in this case, our major axis has a length of 12 units. The minor axis, doubling our b value, we should see that we get a length of 8 for that. The vertices, again, are the endpoints of the major axis. So on this graph here, we'd be looking at this point and this point that we had plotted earlier. And looking at our graph, it should be easy to identify those. Those are simply the points 4, 0, and negative 8, 0. And next we want to identify the coordinates of the foci. And so again, we take C to be the square root of the difference of the denominators of the original equation. So I want to make sure I'm doing 36 minus 16 this time, which gives me the square root of 20. And so we don't want to leave our answer like this. We need to reduce this radical. So remember that 20 we can split up into 4 times 5. So that can be reduced to 2 times radical 5. Now again, the c value that we just found here is the distance from the center to each focus. So to actually find the coordinates of the foci, we want to start from the center and we want to go 2√5 units in the direction of the major axis, which means that we're going to be going left and right from the center this time. Well, remember that the center was at -2, 0. But if we're going 2√5 units to the left and right of that, that means we're going to take the 2√5 and add it to the x-coordinate. We're also going to subtract it from the x-coordinate. Adding the 2√5 is going to take us 2√5 units to the right. Subtracting 2√5 takes us 2√5 units from the left. And so I'm adding and subtracting from the x-coordinate because I want to be going in the x direction. I want to be moving horizontally. I need to be going left and right from the center. And so you don't have to write the foci as separate points like this. If you prefer, feel free to use plus-minus notation. So if you want to write this as -2 plus or minus 2√5, comma 0, that would be acceptable as well. And very often you'll see examples written this way in the textbook. But notice that the y-coordinate does not change. It's 0 for both of them because that was the y-coordinate of the center. And since we were just moving left and right from the center, we just changed the x-coordinate. Another example is if we're moving up and down from the center, then we would only change the y-coordinate. But those are the coordinates for the foci for this example. And so let's try one more example of just working with a basic equation of an ellipse. But if we have x plus 1 squared over 9 plus y plus 2 squared over 36 is equal to 1. Well, again, the first thing we need to do is to identify the center. So in this case, our center is at -1, -2. A in this case will be 3, and B will be 6. Hopefully it's easy to see how I'm getting those numbers at this point. So we'll go ahead and take a look at our graph. So again, center at -1, -2. A we said was 3, so we're going to the right 3 and to the left 3. B is 6, so we're going to go up 6 units and down 6 units. Oops. Okay, so connecting these 4 points, we'll get the graph of our ellipse. So it should look something like this. Okay, and so again, looking at the features of the graph, we have a major axis with a length of 12 units and a minor axis with a length of 6 units. The vertices, once again, these are the endpoints of the major axis. So hopefully we can see that those would be at the points -1, 4 and -1, -8. And again, to find the foci, we're going to take c to be the square root of the difference of the denominators. So I'm going to take 36 minus 9. That will give me square root of 27, which remember we can split up into 9 times 3. So we end up with 3√3. But again, this only gives us the distance from the center to each focus. It doesn't actually give us the coordinates of the foci. So let's actually list the coordinates now. So this time our major axis is vertical, and so the vertices are above and below the center. So the foci should also be above and below the center. That means we need to take the 3√3 that we just found and add and subtract from the y-coordinate of the center, not the x-coordinate. So remember, the center was at -1, -2. But now what I want to do is I want to add and subtract the 3√3 from the y-coordinate of the center. So again, we're always starting from the center, so we take whatever its coordinates are, and we simply add and subtract our c value from either the x or y coordinate, depending on which direction we're going. So in this case, we're going up and down from the center. That's going in the y direction. So we add and subtract from the y coordinate of the center. But you always need to make sure you do this when you're identifying the actual coordinates of each of the foci. So with ellipses, we also need to take a look at equations where we have to rewrite them in standard form as well. And just like with circles, this will involve completing the square. So we'll go ahead and take a look at an example here. Suppose we have 4x squared plus 9y squared minus 8x plus 36y plus 4 equals 0. So for starters, how do we know that this is an ellipse as opposed to just a circle? Well, the thing that'll give it away is when you look at the x squared and y squared terms themselves. For starters, there will be both of them, and we will always be adding them together, as opposed to hyperbolas, which we'll see in another video where we're subtracting them instead. But also notice that the coefficients are different. For the x squared, you have a coefficient of 4. For the y squared, you have a coefficient of 9. When that happens, you'll be dealing with an ellipse. If the coefficients were the same, if they were both 4 or both 9, then we would be dealing with a circle. So when they're different like this, then we know that it is an ellipse. Anyway, the rest of the procedure here as far as completing the square to rewrite in standard form is much like what we saw already with the examples of circles. So I'm going to start by regrouping the x and y terms. And the constant term, the plus 4 that I see at the end, I'm just going to subtract that over to kind of get it out of the way, so to speak. Now, in order to complete the square here, notice that we have the 4x squared and the 9y squared, but completing the square only works when we have just a plain old x squared and y squared term. What that means is that for the x terms, we're going to need to factor out the 4 that we see, which would give us x squared minus 2x. And for the y terms, we will need to factor out the 9, which will give us y squared plus 4y. This always needs to be done before we can complete the square. And again, our purpose is to make it so that the first term is just x squared and just y squared on each of these things. Okay, so then from here, as far as completing the square, just like we saw before, for the x terms, we need to take the negative 2, divide that by 2. That, of course, gives us negative 1. And then we're squaring that result, gives us positive 1. So that's what I'm adding to the x terms, is plus 1. However, what I've really done to the equation is I've added 4, because all of the terms inside the parentheses here, we would need to distribute the 4 to each of them. That means that the 4 would need to get multiplied by the positive 1 that we just added. And what that means is that on the other side here, I'm going to need to add 4. So I do not simply add 1, I need to add 4 to each side. For the y terms, we follow a similar pattern. I complete the square by first taking half of my coefficient of y, so half of that would be 2, and then again we square the result, which gives us 4. So inside here I will need to add 4 in order to complete the square. But again, just like with the x terms, this 9 needs to be distributed to each of the terms in the parentheses, which means that we've really added 9 times 4, so we've added 36. And that needs to be added to the other side as well. So for the most part, it's the same as what we did with circles, but there is this extra thing of keeping track of the numbers that we factor out before we complete the square. At any rate, we can go ahead and factor each of these things now. So I'm going to have 4 times x minus 1 squared plus 9 times y plus 2 squared. And on the other side, we're going to be left with 36. Now we're not quite finished putting this in standard form yet. Remember that when we look at the standard equation of an ellipse, the right-hand side needs to be 1. We don't want 36 there. So to take care of that, we simply have to divide it by 36. But if I divide that by 36, that means I need to divide everything by 36. So simplifying each of these terms, I should now have x minus 1 squared over 9 plus y plus 2 squared over 4 is equal to 1. And so that gives me the equation of this ellipse in standard form. We could easily identify the center as well as the a and b values, and of course use that information to graph it and describe all the various features, including the major and minor axes and foci and so forth. So I'll let you take it from there as far as graphing it and doing all of those other things. But that's how we write the equation in standard form. So we'll try one more example of this sort of thing. So let's do the same process for the equation 25x squared plus 2y squared minus 4y minus 48 is equal to 0. And so as before, I want to group up the x terms from the y terms. So we're going to have 25x squared, and then I'll have 2y squared minus 4y. The minus 48, I'm going to add that over to the other side to sort of get it out of the way. And then I want to factor a 2 from the y terms. So I'm going to have y squared minus 2y, and that is all still equal to 48. So notice that for the x terms, we just have 25x squared. So there's no need to complete the square there. We only have to do that if we have just an x term. Since we don't have that, we just have the x squared term. Basically, the square is already complete for that. However, we still need to complete the square for the y terms. And so hopefully it's not too difficult to tell that we would need to add 1 inside the parentheses here. But again, this 2 we need to imagine as being distributed to all these terms. So we've really added 2 to the equation. So I need to add 2 to the other side as well. So now I can rewrite this expression as 25x squared plus 2 times y minus 1, that whole quantity squared. And on the other side we have 50. And again, we need the right-hand side to be 1, so I'm going to divide each term by 50. So this will now leave us with x squared over 2 plus y minus 1 squared over 25 is equal to 1. So notice in this case that when you identify the center, you would have the point 0, 1. But also notice that in this case, the a value would actually be the square root of 2. And b, of course, would still be 5. So when you're graphing these sort of things, you can go ahead and use a calculator to approximate the square root of 2 for identifying the length of the axis in that direction. But notice that it does have to be a radical here, since a squared itself is equal to 2. But feel free to use a calculator for approximations if you need to. Finally, let's take a look at some examples where we sort of work backwards. So these will be problems where they give us information about the graph, and we use that information in order to find the equation. So suppose we are told that the vertices of our ellipse are the points plus or minus 6, 0, and that its foci are the points plus or minus 5, 0. What we're going to do is we're going to find the equation of this ellipse. So how would we do that? Let's go ahead and take a look at the graph first. This will kind of help us to get our bearings and can make things easier to figure out. So plotting our points on an ordinary set of x and y axes, we have that the vertices are at 6, 0 and negative 6, 0. So that would be these 2 points here. The foci are at 5, 0 and negative 5, 0, which would be here. Well, what this shows me is that the major axis of the ellipse would be horizontal. And so the graph would have to look something like this. So not a very well-drawn graph, but hopefully we get the idea of what we're talking about here. So notice I was not very specific about the b value. So I don't know exactly how far up and down from the center we would need to go. I was just sort of guesstimating as I drew it. But again, the idea here is just for me to get an idea of the ellipse that I'm dealing with. But this does tell me something very important. Hopefully it's not too difficult to tell that the center of this thing would be at 0, 0, because it would have to be in the middle of all these points that I've just drawn. So we know that h and k would both be 0. Furthermore, I know the a and c values that I'm working with. So remember that a gives us the distance from the center to each vertex. So in this case, we can see that our a value would be 6. The c value, on the other hand, that gives us the distance from the center to each focus. So in this case, we can see, hopefully, that the c value is going to be equal to 5. So we know that c is 5, and we know that a is 6. So the only thing that we lack for the equation is our value for b. And so we can figure that out by using the fact that c, in this case, is going to be the square root of a squared minus b squared. So I'm going to plug in the values that I've just found in order to determine what our b squared value will be. So a we know is 6, so we have 6 squared minus b squared in the radical here. And to solve this, we want to square both sides. So what I'll have here is 25 is equal to 6 squared, which of course is 36, minus b squared. And now I can just subtract 36 from each side. So that will give us negative 11 is equal to negative b squared. And so b squared itself will be equal to 11. Now I'm actually going to stop there. I'm not going to bother taking the square root of both sides. And that is because when we look at this standard equation, we don't need to know what b itself is. We just need to know b squared. So remember that our equation is x minus h squared over a squared plus y minus k squared over b squared is equal to 1. Well, now I know everything that I need for this equation to be filled out. So h and k we said are both 0, so that means in our numerators we'll just have x squared and y squared. The a value we said was 6, and so that means in the denominator here we have a squared, which is 36. B squared we've just discovered is equal to 11, so I can plug that in for b squared, and we know all of this is equal to 1. And so that gives us the equation that we need based upon the information that we were given. And so it's just a matter of understanding how all the different pieces of the equation fit together when we're being given information about the graph and trying to work backwards to find that equation. And so let's try one more example like this. Suppose this time we're told that the vertices of our ellipse are the points 0, negative 2, and 6, negative 2. And suppose we know that the foci are at 2, negative 2, and 4, negative 2. So again, let's find the equation of this ellipse, just like we had done with the last example. So again, I think it's helpful to start by actually looking at the graph. So we'll go ahead and do that first. Going ahead and plotting our points here, we have our vertices are at 0, negative 2, and 6, negative 2, so that would be these 2 points here. The foci are at 2, negative 2, and 4, negative 2. And so again, I can see that my ellipse is going to be elongated horizontally. In other words, it'll have a horizontal major axis, because we know that the endpoints of the major axis are the vertices. Okay, well again, we should be able to identify the coordinates of the center here by just looking at the center of our diagram, basically. So hopefully it's not too hard to tell that the center of this ellipse is going to be at the point 3, negative 2. And so those would be our coordinates for h and k. That's one of the ways that drawing the graph first can be helpful, is identifying the center. But also notice in this case that our a value, that's the distance from the center to the vertex, is going to be 3. You can see that it's just 3 units from the center to each vertex. Our c value, again, is the distance from the center to each focus. Well, each of the foci, they're just 1 unit away from the center. So that means that c will be equal to 1. And so, as with the last example, using the fact that c will be equal to the square root of a squared minus b squared here, we can just plug these numbers in order to figure out what b squared will be. So solving this equation again, we simply have to square each side. So that will give us 1 is equal to 9 minus b squared. And if you go through and solve for b squared here, I'll let you do the math on your own, but you should get that b squared is equal to 8. And so again, looking at our equation here, we know that it's x minus h squared over a squared plus y minus k squared over b squared is equal to 1. And as we said, h and k were located at 3 and -2, so that's going to give us x minus 3 squared, and then we're going to have y plus 2 squared. The x minus 3 squared, we need to divide that by a squared, so since a we know is 3, that means that a squared is 9. B squared, we've just found, is equal to 8. And so all of that we can set equal to 1. So that gives us our equation for this ellipse. Okay, I do want to take a look at just one last type of example that can be a little bit perplexing when you first see this sort of thing in the homework. But suppose I had the equation, let's say 16 times x minus 1 squared plus 9 times y plus 1 squared is equal to 1. Well, this equation technically is already written in standard form. What we want to do, though, is to rewrite it in a way that we can easily identify the a and b values. So what we want to notice here is that with the x terms, we're multiplying by 16. That is actually the same, though, as dividing by 1 over 16. And so I'm going to rewrite the first term in this form here so that I can easily identify that a squared is 1/16. Then I do the same thing for the y terms. We have y plus 1 squared. I can divide that by 1 over 9. That would be the same thing as multiplying by 9. And so for an example like this, the center would be the point 1, -1. And for our a and b values, we know that a, or I should say a squared, is 1/16. And so that means that a would be 1/4. For our b values, we know that b squared is 1/9. And so that means that b would be 1/3. So what this means is that when you look at the lengths of the major and minor axes, the major axis would come from our b value. Since b is larger than a in this case, the major axis would be 2 times that, so it would have a length of 2/3. And the minor axis would have a length of 2 times 1/4, which would be 1/2. As far as identifying the coordinates of the foci, we'd still use the value of c, which would be equal to square root of, in this case, b squared minus a squared. So we would take the square root of 1/9 minus 1/16. So subtracting these, you'll end up with 7 over 144, and so simplifying that, you get square root of 7 over 12. And so that means that the coordinates of the foci, since we'll be going in the b direction here, we would take the coordinates of the center, which were at 1, -1, and we would take the y value and add and subtract the c value. So the coordinates of the foci would be 1 and then -1 plus or minus root 7 over 12.